think about back in the pressure field. This is the contour of the pressure field. What does this look like? This looks like a series, a series of oblique shocks, right? That emanates from the upper side of the airfoil. Okay, in reality, these could be shocks if the pressure increases, right, over the contour. If the contour is a contour of increasing pressure, or if the contour is a contour of decreasing pressure, that's what we call expansion waves. That's kind of the opposite of shock waves. And the nonlinear behavior of shock waves and expansion waves are actually different. As we are going to see, the expansion waves cannot form discontinuities. While shock waves are very thin, expansion waves are always expanded over a spatial region. But as we take the perturbation goes to small, right, when the strength of the shocks and expansions are infinitesimal, they actually behave the same, right? So they are just contour lines that's at a fixed angle and of constant pressure. Yes?
These are all, each line is a different pressure value.
Yes. Each line is a different pressure value, that's right.
Is it increasing or like?
It could be increasing or decreasing, right, depending on what this F is. Yeah, so these are, for example, this is F0, this is F1, right? So if F1 is greater than F0, then the pressure is increasing. If F1 is less than F0, then the pressure is decreasing, right? But the contours always look like that. All right.
So the Mach number just stipulates what shape the ISO lines make.
Yes, the Mach number actually determines what the ISO lines or what the contours are sloped towards. So let's, for example, look at a different scenario where the Mach number is higher. Let's say m is equal to, how can I make good integers? Oh, let's just forget about it. M is equal to 2, right? So square root of m squared minus 1 is about square root of 3, right? Or 1.7-ish. Okay, so now how would the contour look like? When x is equal to, so let's look at in this case, what is F0? What is the ISO line that makes the pressure equal to F0? Yes, x needs to be slightly larger than z, right? X needs to be a factor of 1.7 larger than z. So the ISO lines would go slope more towards the horizontal direction. All the shock and expansion waves hug the airplane more, right? So that's the effect of a higher Mach number. Yes?
Wait, what was the last sentence? You said those shocks say help or hurt there?
The shock waves what? Yeah, the shock waves would kind of hug the airplane closer, right? They kind of go towards the airplane. Yeah, at the hypersonic speeds, when Mach number is like 5, 7 or something, the shock waves would be so close to the airplane that so like it would be very close to the airplane, sometimes even just outside the boundary layer. Okay, so that's for the solution where the sign is minus. The solution where the F is going to be plus is very similar. Except for the same, that's, I think I denoted this as G. So that's going to be a different solution. Except for, let's actually extend the axis a little bit. When X increases, G has to decrease, right, for the value to stay the same. So as X increases, G would decrease, so you get ISO lines like that. So that's waves emanating from the underside of the airfoil. Okay, and actually at some point, let's say this is the end of the airfoil, this would be the last wave emanating, and afterwards there won't be any there won't be anything that would trigger the solution to become different, right? So the reason you have a intersection here is that on this line we don't have to satisfy the equation because that's occupied by the airfoil, right? You don't. I mean, the equation we wrote only has to be satisfied in space occupied by air, right? If you have an airfoil over here, inside the airfoil it's solid, and you don't need to satisfy the equations. So we don't need, although if you look strictly at the solution, if we have to satisfy the solution everywhere, the red lines would actually extend further, right, at the negative z. But it doesn't have to, because inside of the black region is the airfoil. The equation doesn't have to be satisfied. Similarly, if you look at the green solution, if the equation has to be satisfied everywhere, the green lines would extend like that way, right? But it doesn't have to, because inside the airfoil it doesn't satisfy the equations. But after the end of the airfoil, there is nothing that would prevent you from having to satisfy the equations. So you couldn't really have any solution here. Otherwise, the solution would extend all the way to infinity upstream, and that couldn't happen because the equations are hyperbolic, right? Over here, there couldn't be, the solution over here cannot be affected by the presence of the airfoil. All right. Okay. Any questions? Yeah. No. Yes.
So we're assuming this function has that different things.
Yes. So now the question is, the solution to the differential equation only tells us, right? The solution follows. The solution up there satisfies some f, and the solution down there satisfies this form for some g. It doesn't tell us yet what f and g is. Okay. Or how does the shape of the airfoil determines the function form of f and function form of g? That's the thing we'll have to look at next. Okay, that is what determines the function f and g, and to see that we have to look at how the velocity, not just the pressure, would behave as the pressure increases and decreases over these isolines. Okay, and only after we understand how the velocity behaves, we can understand how the shape of the airfoil would determine this f and g, the solution to the equations.